Hello, my name is Matthew, and today I want to go over a situation where we have a cylindrical tank, and that tank has some liquid within it. And when we spin the tank, that liquid will start to climb up the walls of our tank and eventually spill over, right? And so we have our liquid at rest here, and we're going to assume that the radius of our system is equal to the height of the liquid within it. And then it also has some height as well. So then we have our system here after we've given it some angular frequency, after we start to spin it. And a cross-sectional view of that tank will reveal that the liquid makes a parabola shape. So there has to be some maximum angular frequency that we can give our system so that the liquid just reaches the top of our tank, but doesn't spill out. And so that's what we're going to figure out today, is what that maximum angular frequency is. So we'll go ahead and start out with an equation from statics. We'll say the changing of pressure over with respect to the radius is going to be equal to the density of our system, of our liquid, times its angular frequency times the radius. Of course, we can rearrange to the changing of pressure being equal to the density angular frequency squared and radius times the changing of the radius. Now, integrating both sides, we'll get that the pressure is equal to the density times angular frequency squared times radius squared all over 2. And that's just expressing the pressure in the horizontal direction here, right? Because it's with respect to radius. But we know that pressure is equal in all directions, and so we can actually express it in the vertical direction as well. And so if we do that, we can just, to do that, it is just the density times our force of gravity times the height of the liquid within the system. And so we can see that densities cancel, and we can find an expression for the height of our liquid. And so that will be very important. So the height of our liquid is going to be equal to the angular frequency squared times the radius squared, all divided by 2 times the force of gravity. So that's important. Now, if we look at the volume of our tank and our liquid, we can see that if we draw a line from here that the volume is below the line, so the volume below the parabola here is equal to the volume below that same line down here. So these two volumes are equal, right? So these volumes also must be equal because we're not having any liquid spill out of the system. So I'll go ahead and color in those areas. But being able to relate these two volumes is going to make this calculation possible. So these two volumes are equal to each other. And so we can easily find the volume of this segment here, and then solving for this volume is a little bit more complicated. But first, we'll solve for this volume. And of course, we know that it's a cylindrical tank, so the volume has to be equal to, of course, the base times the height. The base is going to be a circle, so pi r squared, times the height of that volume right here. So now we need to set a new variable, or define a new variable. We're just going to call it the height of the blue section when our tank is stationary. So that height right there of the blue section is just going to be called d. And we've gone ahead and defined that ourselves. So the volume of this blue section is going to be equal to pi r squared times d. Now what about finding the volume for this blue section? Well, it's a little more complicated, but we can look at it under this angle. So we're looking at just the parabola. And if we want to find the volume of, say, this tiny little area here, we can add up all the individual volumes at each respective radius and end up finding the total volume, right? And so from here all the way out to here, that's 0, and then this is our maximum radius r, right? And so if we want to find this, we can just take the integral from 0 to the maximum radius of r, and well, the volume of this tiny little segment here, well, it has a thickness of dr, changing in radius, and then we multiply it by the circumference of a circle and the height of that segment, then we can find the volume. And so the integral from 0 to r of the circumference of a circle, so 2 pi r, times the height of that segment times the changing of the radius is equal to the changing of the volume, the integral of the changing of the volume, right? And so taking this integral and taking this one, we'll get another expression for volume. And it will be equal to, well, first we have to substitute in this, right? And so this becomes 0 to r, 2 pi r times the angular frequency squared times the radius squared, all over 2g, and then that is with respect to changing of our radius. And that ends up being equal to the angular frequency squared times pi times the maximum radius to the power 4 divided by our force of gravity, 4 times the force of gravity, so 4g. So now we have these two equations for volume, and we can solve for d here, because we set them equal, say, the angular frequency squared times the radius to the 4th power times pi, all over 4 times the force of gravity. These are just our two volume equations here. Of course, we get some nice cancellations, and we'll find that our variable d is equal to the angular frequency squared times the radius squared, all over 4 times the force of gravity. Right? And so going back over here, we know that we want to find the angular frequency so that the water reaches the maximum height of our system but doesn't spill over. And so the maximum, or the height of our system, is equal to the height of our system is equal to the height of our water's parabola here, and that's just going to be found with our height function down here. And we're going to take this function when it's at the maximum radius. So go ahead and say r, the maximum radius. So that's just that segment, plus this segment here. Well, what is this segment? This segment is just the difference between r and d, right? So if we take r and subtract d, we'll get this segment, right? So plus r minus d. Right? And so we can move r over here. We'll get h minus r is equal to our height function evaluated at the maximum radius minus d. And of course, we can evaluate this height function, and we know what d is equal to, and we can put them both in the same, in terms of the same variables. So we'll have h minus r is equal to h of the height of our liquid evaluated at the maximum radius. So angular frequency times the maximum radius squared all over 2g. And then now we're subtracting our d variable here, which is the angular frequency squared times the radius squared all over 4g. And so simplifying this, we'll just get the angular frequency times the radius squared divided by 4g. So I'll go ahead and erase and write that out. So the angular frequency squared times the maximum radius squared all over 4 times the force of gravity. And from here, we can just solve for the angular frequency. And I'll go ahead and do that over here. So the angular frequency just ends up being equal to the 2 times the square root of g times h minus r all over r. So this is our equation here to solve for the maximum rate, or the maximum angular frequency of our liquid, so that the height of the liquid just equals the height of our tank. And it's defined as angular frequency being equal to 2 times the square root of g, the force of gravity, times the height of our tank minus the radius of our tank, all divided by the radius of our tank.